Hey everybody, I'm the Linz in Fizz with Linz, and today we're here to talk about physics graphs. Dun-dun. How'd you like that little jingle? That's on the spot. Yeah, no, that's on the spot. No, I definitely didn't do that in an earlier take because these intros sometimes take me time because I stumble on my words. Today's episode is brought to you by umbrellas. Umbrellas, not just for Rihanna. Umbrellas, they'll keep you dry. Umbrellas, don't use them though if it's too windy, because then it'll go inside out and then it's just like, what do you even do with it after that? Umbrellas. Now let's review something we talked about in a tips and tricks video that we did a little bit ago. If you're looking for that video, check for the link in the description. But we talked about graphs, and there's typically 3 things we would do with graphs when we encounter them in any given physics problem or scenario. And the first thing is reading. If we read the graph, it'll tell us about what's on the vertical axis at a given value for the horizontal axis, right? So we'll have some examples of that in a minute, but I'm just reading what basically values from the vertical axis. The slope, right, would be taking those 2 axes and dividing them, right? And then the third thing we could do is finding the area by multiplying the vertical axis and the horizontal axis together. So let's get some common graphs that frequently pop up on things like AP exams and other summative physics assessments. Well, first is we have the motion graphs, as these are commonly called, and these are typically, you can find them often together. We can find them for motions of objects like rolling down ramps, an object that's thrown, right? Also for oscillators, many different things could fall for these graphs, right? Many different motions. But let's look at the first one, would be a position time graph. And if we read that graph, we'd get positions and their associated time values, because it's a position graph, so it tells us about positions. If we slope this one, though, it'd be position divided by time, which we would call rate of motion, also known as velocity, right? And remember here, it is velocity. Speed would be the absolute value or the magnitude of this number. This graph, we wouldn't do area for this graph. I'm not saying it doesn't mean anything. I'm just saying it's not something that we would commonly do or that it has any use for us, so we would just sort of ignore that. Next graph up is our velocity time graph, and if we read it, we would get velocity, because that's what happens when you read the graph. You get what the graph is. If we slope this graph, we would get acceleration. Because again, it would be the rate of change of the rate of motion, also known as acceleration. And this graph, if we take the area of this, we would find the displacement of the object. Please note that here the area could be positive or negative, and that would be really important in a given problem. Now, our last graph up for the motion graphs would be the acceleration graph. And if we read it, we would get accelerations. I'm noticing a trend with reading, right? If we would slope this graph, we wouldn't. It absolutely has a physics meaning, but it's not something we typically do at our level. And then the area is actually change in velocity here. Now, that area for this acceleration graph isn't used very regularly, so it's not something we talk about a whole bunch. Now, the next main set of graphs that we'll frequently correlate to is still about motion of objects, but that's correlated now to the force. So the first one would be force displacement graph, right? And if I have a force displacement graph, well, if I read it, it would give me the forces. If I sloped this, we wouldn't. And if I found the area of this, it would be the work or the change in energy. My note here that would be important is it would be a singular form of energy that would be changing in this scenario, because we're talking about typically a one-object system, not a multi-object system. So it could be something like a car jamming on the brakes, right? And that would be then the kinetic energy is what's changing. So it'd be delta K, right? It also could be something along the lines of an object falling or an object being picked up as well. But now we can actually have force displacement graphs that mean different things-ish if they involve springs. So if the graph is from a spring type experiment, students are stretching a spring and creating a graph from it, then if we read this, well, we'd still get forces. But if we slope this graph, we'd get the spring constant. Also, can we just appreciate how artsy that spring shot is? Thank you, Image Search. Just like spring's day out on like a bench somewhere. Like, oh, he's enjoying the weather. And if we area this, again, it'd be work is change in energy. But that most likely would be correlated to the springs, right? We're stretching the spring, and it would be correlated to the amount of spring potential that is in that spring system. The last graph on this set would be force time graphs. Now, if we see one of these ones, if we read it, we would get forces, because, yeah. And we wouldn't slope this force per time, be like a rate of force, which is not something we talk about. But then area of this would be impulse or change in momentum. This is a big one for us. We see this graph a whole heck of a lot. We want to make sure we understand that when we see a force graph, right, that area would give us fat, right? Force times time would be super important. Then we could correlate to impulse, and we could take that impulse, right, change in momentum, and we could use that to find a final velocity and initial velocity, right? Or we could just find the change in momentum of a given system. Hope this helped. Use these strategies, this read, slope, and area tricks for any graph you encounter at any time. Hope you found this helpful. Smash that like and subscribe. Hit the bell for more videos like this. Drop a comment if you're digging these. You don't have to. That felt. You don't have to drop. No, you don't have to leave a comment. It's okay. No, it's fine. It's fine. Like I don't like need the comments. It's not like I'm like reading them. You know, like it's not like I'm like waiting here, like just waiting for a comment to pop up. It's not. No, I'm not. Until next time. Whenever I say that, Alexa pops on like every time. Until next time. That time she didn't. Just hit the outro.